Hello again, and welcome back to our video series on astronomy. My name is Mr. Nelms. I'm one of the physics and astronomy teachers here at Haberdashers Adams. This is the fourth episode in our series on the moon. This time we will be looking at the near and far sides of the moon, comparing their features and looking at why they are different.
3, 2, 1.
We choose to go to the moon.
For the vast majority of human history, we have only ever seen about half of the moon, the near side. This is because the moon is tidally locked in its orbit of the Earth.
This means that the time taken for the moon to rotate through a 360-degree angle is the same time for it to complete one full orbit of the Earth. As a result of this, the same side of the moon always faces the Earth and has done for almost all of its history.
The first time that we saw the far side of the moon was in October of 1959, when the Luna 3 spacecraft took photos of it during its flight, whilst the craft used the lunar gravity to slingshot itself back towards Earth.
The mission itself was the first to achieve a gravity assist, a manoeuvre probably most famously utilised by the Apollo 13 mission after they encountered a failure in one of their oxygen tanks en route to the moon. Sadly, as impressive as the flight path was, the quality of the images was not exactly great. Despite the poor quality, though, it was clear that the far side of the moon featured much less Maria than the near side and much more Terrae. The quality of our mapping improved significantly over the next decade, with the Zond 3 mission in 1965 allowing the Soviets to map the far side in much greater detail. The Americans continued to further this, first with the Lunar Orbiter program, and then with the first photos of the far side of the moon taken by manned spacecrafts from Apollo 8 onwards.
In total, only 24 men have seen the far side of the moon in person, these being the astronauts from the Apollo 8 through to 17 missions. Since the end of 1972, though, no manned missions have been to the moon, meaning that the only footage we have from the last 50 years is from unmanned craft.
When we compare the two sides of the moon, it is clear that there are huge differences between them. We have analysed the near side in detail in our last episode. Check that out to see this in more detail. But even from a quick glance, it is clear that the near side has significantly more Maria than the far side, and that the far side is much more heavily cratered. To understand why this is, though, we need to understand the process by which the moon formed. There have been several theories as to how the moon formed, but the leading theory is that shortly after the Earth formed, a Mars-sized object collided with it. The force of the collision turned both objects molten and resulted in the moon orbiting at a distance much closer than it does now. Due to the close nature of the initial orbit, the moon became tidally locked. This meant that it quickly settled into having only one side facing the Earth. This had knock-on effects on the cooling of the moon, as the near side was closer to the still molten Earth, and so cooled down much slower than the far side of the moon, which was exposed more to outer space. The crust on the far side of the moon has an average thickness of around 100 kilometres, whereas the near side of the moon has a crust of only 60 kilometres thick. It is thought that this also led to the moon's core being off-centre by approximately 2 kilometres, though this doesn't feed much into the surface features. During the later heavy bombardment period of the solar system, the far side of the moon seems to have been hit much more frequently by objects which had had their orbits destabilised due to some gas giants, notably Jupiter, which wasn't quite settled in their own orbit. On top of this, when the moon went through its volcanic phase, the lava flows found it much easier to reach the surface on the near side of the moon due to the significantly thinner crust. This led to large portions of the near side being covered in Maria, whereas the lava had a further 40 kilometres to travel through on the far side of the moon to get to the surface, allowing for much fewer Maria to form. The formation of a greater number of Maria on the near side of the Moon may have also masked how big or small the difference in crater formation was during heavy bombardment, as many of these older craters were filled in on the near side of the Moon.
One benefit for us as astronomers is that when we observe the near side of the Moon, we can get a rough estimate of the relative ages of craters based on their location. Those that form on the Maria are likely much younger, having formed far more recently than during the heavy bombardment phase. On the other hand, when trying to age the craters on the far side of the Moon, this is a much trickier prospect. To understand the differences between the two sides of the Moon in greater detail, more research will need to be undertaken, either from satellite imagery or from experiments on or under the lunar surface. As astronomers, understanding the Moon's formation and how the lunar surface evolved is of great importance, as aspects of this evolution will mirror how the early Earth evolved and cooled following the formation of the Moon, only on a differing timescale due to the relative sizes of the two bodies.
If you want to further your knowledge on this subject, here are 3 questions to help you on your way. 1. What other effects have come from the Moon being tidally locked? 2. Why did the lunar orbit become more distant over time? And 3. How might the different cooling times of the Earth and Moon impacted on their other features? A massive thank you to everyone who's joined us on this journey so far, and we hope you'll join us again for the next and final episode on the Moon, which will cover one of the more challenging concepts to understand about the Moon's orbit, which is lunar libration. Until then, watch this space.